Imagine taking, a trusted pill every single day for 30 years.
Right, like something you just keep in your purse or your glove box without a second thought.
Exactly. You keep it in your bathroom cabinet, you give it to your family. I mean, it's one of the best-selling, most universally accepted over-the-counter medications on the planet.
A total household name.
Yeah. And then, abruptly, you find out that while it was just sitting there in the warmth of your bathroom, the actual chemical structure of the pill was, well, quietly degrading into a probable human carcinogen.
It's honestly a terrifying scenario.
It really is. So today, for our deep dive, we are looking at the rise, the dominance, and in one particular case, the catastrophic fall of a class of drugs that completely revolutionized how we treat stomach acid.
Yeah.
I'm talking about H2 receptor blockers.
And, it's a profound shift in perspective when you look at the actual mechanics of these drugs, rather than just the relief they provide.
Right, because most people don't think about the biological machinery causing their heartburn. They just want the burning to stop.
Exactly. But understanding how different pills interact with that machinery, it reveals so much about how our bodies are wired.
Okay, let's frame it this way for you listening. Picture your stomach as this massive, highly regulated chemical factory.
I like that analogy.
Yeah, so when you take a standard antacid, think of like a Tums or a Rolaids, you're essentially just throwing down a mop to clean up a corrosive spill that is already on the factory floor.
Right. It temporarily neutralizes the acid sitting there, but the machines are still running.
Exactly. Then you have proton pump inhibitors, or PPIs, like omeprazole. Taking a PPI is like walking into the factory and physically yanking the power plug out of the acid manufacturing machines.
The machines just go dead, which is, an incredibly effective brute force approach. But it happens at the very end of the biological assembly line.
Okay, let's unpack this, because H2 blockers do something far more elegant. They don't mop up the spill and they don't yank the power cord.
They do something earlier in the process.
Right. Instead, they intercept the floor manager's memo that tells the machines to turn on in the first place. They are like signal interceptors.
That's a great way to put it.
And that distinction between neutralizing acid, unclogging the pump, and blocking the incoming signal is really the conceptual anchor for this entire deep dive.
It is. And to understand how we learn to intercept that specific chemical memo, we actually need to look at how pharmacology functioned prior to the 1960s.
Because it was basically the Wild West, right?
Pretty much. Historically, developing a new drug was heavily reliant on luck. Scientists would just screen thousands of natural compounds from plants, soil, or molds.
Just hoping to see something happen.
Exactly. Yeah. Hoping to observe a desired effect, often without even understanding the underlying mechanism. It was a massive game of trial and error.
Enter Sir James Black in the 1960s. He was working at the pharmaceutical companies SmithKline and French in England, and he fundamentally rejected that trial and error approach.
He really did. He believed in what we now call rational drug design. And he had already proven it could work, actually.
Oh, right, by inventing propranolol, the first successful beta blocker for the heart.
Exactly. Black recognized that if adrenaline was the chemical key making the heart beat faster by fitting into specific beta receptors, he didn't need to search the jungle for a random plant to slow the heart down.
He could just make a fake key.
Basically, yeah.
Yeah.
He could deliberately engineer a molecule in the lab that was shaped just similarly enough to fit into the lock, but without turning it.
A broken key, essentially, that blocks the real key from entering.
Right. And he turned around and applied that exact same logic to stomach acid.
Which makes sense. But at the time, researchers knew a chemical called histamine stimulated the stomach to churn out acid.
They did. But there was this glaring contradiction that confused everyone.
Right, because conventional antihistamines, like the allergy medicines we take for sneezing and hives, they did absolutely nothing to stop stomach acid.
And this is where Black's genius really shows.
Mm-hmm.
He deduced the missing variable. He reasoned that if histamine drives both allergic reactions and stomach acid production, but allergy medication only stops the sneezing.
Then histamine must be interacting with two completely different structural locks in the body.
Exactly. He proposed calling the known allergy lock the H1 receptor, and he hypothesized the existence of a second, undiscovered lock in the stomach.
Which he named the H2 receptor. Wait, I actually have to pause here, because this completely upended my understanding of how these drugs relate to each other.
It's a surprising connection, isn't it?
It really is. Allergy antihistamines and stomach acid blockers are chemical cousins. I mean, they are blocking different receptor subtypes of the exact same underlying chemical signal in our bodies.
They are. But the challenge back then was that no one knew what this theoretical H2 lock actually looked like.
Right, you can't build a key for a lock you can't see.
So Black and his chemist colleague, C. Robin Ganellan, had to work backward. They used the histamine molecule itself as their starting blueprint.
And it took them, what, like a decade?
Roughly 10 years, yeah.
Yeah.
They systematically modified histamine, adding a chemical group here, removing one there. They tested hundreds of variations to find a molecule that would sit in the H2 lock without actually activating it.
Which led them through several prototypes. I think the notes mentioned compounds named barimamide and mediamide before they finally synthesized cimetidine.
Yes, cimetidine, which was eventually marketed under the brand name Tagamet, launching in the late 1970s.
And this wasn't just a win for heartburn sufferers. This was the ultimate proof of concept for rational drug design.
What's fascinating here is that you figure out the receptor, you engineer the blocker. Black's work literally reshaped the pharmaceutical industry. I mean, it eventually earned him a Nobel Prize.
Wow.
Yeah.
But the true elegance of what Black built, I think, only becomes clear when you look at the microscopic environment of the stomach lining itself.
Absolutely. The specialized cells responsible for pumping out acid are called parietal cells.
And reading through the biology for this deep dive, what really struck me is that parietal cells do not have a simple on and off switch.
No, they are much more complex than that.
Right. There are three distinct, completely separate input lines sitting on the surface of the cell, all converted internally on a single acid-making machine, the proton pump.
And we can break those three inputs down by where they actually come from. The first is a local hormonal signal, histamine.
Which is released by specialized neighboring cells right there in the stomach lining.
Right. Then the second is a systemic hormonal signal, gastrin. Your body releases gastrin into the bloodstream when food physically stretches the stomach or, when it detects proteins that need breaking down.
Okay, but the third one really threw me for a loop. It's a direct neural connection via the vagus nerve.
Yes, the vagus nerve is incredibly powerful.
The chemical signal is acetylcholine. This means your brain can literally tell your stomach to make acid before food even hits your mouth.
It's the anticipation phase.
Right, like just smelling a pizza or even anticipating a big meal sends acetylcholine down the vagus nerve to jumpstart the acid pumps.
Which sets up a really fascinating biological puzzle.
Here's where it gets really interesting, yeah.
If there are three separate signaling pathways, histamine, gastrin, and acetylcholine, all telling the cell to make acid, blocking just one of them shouldn't be revolutionary.
Right, because mathematically, if you block the histamine memo, but the gastrin and acetylcholine memos are still coming through loud and clear, you'd expect maybe a 33% reduction in acid?
That would be the logical assumption, sure.
But the clinical data shows that taking an H2 blocker shuts down 60 to 70% of total acid output. How does blocking 1/3 of the inputs knock out over 2/3 of the acid?
Well, biology rarely follows simple arithmetic. The secret lies in a concept called potentiation.
Potentiation. Okay, unpack that for us.
Histamine isn't just an equal third of the equation. It acts as a necessary amplifier for the other two signals.
Wait, how does it amplify them? Are the other signals physically interacting with histamine?
They're essentially relying on it. So while gastrin and acetylcholine do have their own direct ports on the acid-producing cell, a massive portion of their biological job is actually to walk over to those neighboring histamine-producing cells and kick them into overdrive.
Oh, wow. So when your vagus nerve fires because you smell pizza, the acetylcholine doesn't just tell the acid pump to turn on.
Exactly. It tells the local cells to flood the entire area with histamine.
So histamine is the biological bottleneck. The gastrin and acetylcholine signals are largely being funneled through the histamine pathway.
That's the first principle subtlety of it all. By deploying an H2 blocker to jam the histamine lock, you aren't just silencing one voice.
You are essentially bottlenecking the entire communication network of the stomach.
Exactly. And that bottleneck was so phenomenally effective that the introduction of cimetidine caused a seismic shift in medical practice.
A literal overnight paradigm shift. I mean, before 1977, if you developed a severe bleeding peptic ulcer, the ultimate medical solution was major surgery.
Very invasive surgery, yes.
Surgeons would perform a vagotomy, physically severing the vagus nerve to cut off that acetylcholine signal, or a partial gastrectomy, where they would just cut out the section of the stomach making the acid.
And we suddenly replaced highly invasive mechanical surgeries that carried real mortality risks with just a daily pill.
The economic and clinical impact must have been staggering.
Oh, it was. Cimetidine became the first drug in history to reach $1 billion in annual sales. It basically created the very concept of the pharmaceutical blockbuster.
And the sources outline how doctors aggressively tested the limits of this new chemical bottleneck. They used a rare condition called Zollinger-Ellison syndrome as the ultimate stress test.
Right, Zollinger-Ellison syndrome occurs when a patient develops a tumor that secretes massive, continuous amounts of gastrin.
So the stomach is essentially receiving a blaring, nonstop alarm to produce acid.
Exactly, leading to horrific, life-threatening ulcers. Under normal circumstances, you'd think that much gastrin would just override everything.
Yeah, that the H2 blockers wouldn't stand a chance.
But because of that potentiation effect, because all that gastrin still relies on the histamine pathway to do its worst, doctors discovered that giving these patients massive doses of H2 blockers could actually halt the acid flood and keep them alive.
It proved, in the most extreme clinical environment possible, that intercepting the histamine memo was the master switch.
It did. But, the era of H2 blockers as the definitive cure for ulcers was actually operating on borrowed time.
Because the fundamental understanding of what caused ulcers in the first place was completely wrong.
Right. In 1982, two Australian researchers, Barry Marshall and Robin Warren, challenged the foundational dogma of gastroenterology.
Because the medical consensus at the time was that the stomach was far too acidic to support any bacterial life, right?
Exactly. Ulcers were universally attributed to stress, spicy food, or just excess acid. But Marshall and Warren discovered an acid-tolerant bacterium called Helicobacter pylori living in the stomachs of ulcer patients.
And because the medical establishment basically mocked them and refused to believe bacteria could survive in the stomach, Marshall took matters into his own hands in the most visceral way possible.
He really did. First, he had his own stomach scope to prove it was perfectly healthy.
Okay.
Then, he took a beaker containing a cloudy broth of live H. pylori bacteria cultured from an infected patient, and he just drank it.
Wait, he just drank it, just like that?
Just drank it. He expected to develop an ulcer maybe years down the line, but within days he was suffering from severe nausea and vomiting.
Oh my God.
His stomach lining was massively inflamed. He proved definitively that the bacteria was the instigator. And then, thankfully, he cured himself using standard antibiotics.
That is wild. And that beaker of broth earned them the Nobel Prize in 2005.
It did. If we connect this to the bigger picture, it shifted the entire therapeutic landscape. The goal was no longer suppress the acid indefinitely to manage the ulcer.
Right. The new goal was eradicate the bacterial infection with antibiotics to cure the ulcer.
Exactly. So H2 blockers went from being this miracle cure to serving as a symptom control bridge. You take them to manage the pain while the antibiotics do the actual heavy lifting.
And as that shift happened, the armor of H2 blockers started to show some major cracks, starting with biology actually fighting back against the drug.
Yes, the clinical term for this is tachyphylaxis, or tolerance. You see, our bodies are constantly seeking homeostasis.
Right, balance.
So when an H2 blocker intercepts the histamine signal, acid production plummets. The stomach senses this dramatic drop in acid and essentially panics.
So what does the stomach do? How does it bypass a jammed lock?
It upregulates. The body floods the system with more gastrin, and it physically increases the number of receptors on the cells, just desperately trying to amplify the signal to shout over the H2 blockade.
Wow.
Yeah, within just a few days of continuous use, H2 blockers lose a meaningful percentage of their acid-suppressing power.
And this rapid biological workaround is why proton pump inhibitors, when they arrived in 1989, completely took over the market for chronic conditions like severe GERD.
Precisely. Because a PPI physically disables the final acid pump, it doesn't matter how loudly the stomach shouts with gastrin or acetylcholine. The machinery is broken.
PPIs hold their power over time much better because they are downstream of all the communication.
Right. So H2 blockers lost the crown for chronic severe reflux. But even within the H2 blocker family itself, there was intense internal competition.
Primarily because cimetidine, the original miracle drug, carried some really significant chemical baggage.
It did. It interfered with the liver. Cimetidine is a potent inhibitor of the cytochrome P450 enzyme system.
And these are the liver enzymes responsible for metabolizing other medications, right?
Right, exactly. So if you take cimetidine alongside a blood thinner like warfarin, the cimetidine slows down your liver's ability to clear the warfarin.
Which can dangerously elevate the levels of the blood thinner in your system, leading to hemorrhage risks.
Right. And it also showed anti-androgenic effects at higher doses. It can actually block testosterone from binding to its receptors, which led to reports of gynecomastia, the enlargement of breast tissue in men, and reduced libido.
Yeah, when you are looking for heartburn relief, Disrupting your liver function and your hormones is an absolutely unacceptable trade-off.
which naturally paved the way for the next generation of H2 blockers. Famotidine, most commonly known by the brand name Pepcid, hit the market as a significantly cleaner alternative.
Because it doesn't interfere with the liver's P450 enzymes, and it lacks those anti-androgenic side effects. It basically eclipsed cimetidine entirely.
It did. But the real shock to the pharmaceutical industry wasn't the slow decline of cimetidine. It was the absolute catastrophic failure of another H2 blocker, ranitidine.
Better known as Zantac.
Yes, ranitidine was a titan. For decades, it was one of the most widely used, most trusted over-the-counter medications globally. It was considered the very definition of a safe, boring, everyday drug.
Until September 2019, independent testing labs made a discovery that sent literal shockwaves through the FDA. They found that ranitidine products contained NDMA, which is a probable human carcinogen.
And this wasn't a case of a dirty factory or cross-contamination on a specific assembly line. That is the critical distinction here.
Right. The problem was inherent to the ranitidine molecule itself.
Exactly. The chemical structure of ranitidine contains a nitrate ring. Researchers discovered that when the drug is exposed to higher temperatures, like sitting in a hot car or just aging in a bathroom cabinet over its shelf life, that molecule becomes unstable.
It breaks down.
Yes, it breaks down, and the fragments recombine to form NDMA.
The pill was literally degrading into a cancer-causing agent while sitting in the blister pack. I mean, the FDA launched an investigation, and by April 2020, they pulled the ripcord.
They requested a full, immediate market withdrawal of all ranitidine products.
So what does this all mean? A foundational drug trusted for over 30 years just evaporated from the global market in just 7 months.
It forced a massive, sudden reshuffling of the over-the-counter market. Famotidine basically had to absorb the entire market share overnight.
And this leads to a fascinating, borderline sneaky marketing detail that you might have noticed if you've been in a pharmacy recently. You will still see boxes on the shelf branded as Zantac. Specifically, Zantac 360.
Which causes a tremendous amount of confusion for patients who actually remember the recall.
Because it is not ranitidine. Ranitidine is entirely banned. Zantac 360 is just famotidine repackaged under the old familiar brand name. It's an entirely different active ingredient.
It's a clever, if slightly deceptive, pivot.
It is exactly like buying tickets to see your favorite classic rock band, and you show up to the arena only to realize the lead singer, the drummer, and the guitarist have all been replaced by completely different people. They just legally kept the band's name to sell tickets. You are getting famotidine, not the original Zantac.
The branding survived the scandal, even though the chemical didn't. But, despite the downfall of ranitidine, H2 blockers, primarily famotidine, are not obsolete at all. They fill a very specific, vital niche in modern medicine.
Right, they are the ultimate step-down option. Because as PPIs have been prescribed for longer and longer durations, the medical community has really started to flag potential long-term risks.
They have. When you suppress stomach acid completely for years at a time with a PPI, you can encounter downstream effects. Acid is necessary for absorbing certain nutrients like calcium, magnesium, and vitamin B12.
So long-term PPI use has been associated with things like slight increases in bone fracture risks, potential kidney issues,
And an increased risk of severe gut infections like C. diff, because you've essentially removed the stomach's primary acidic defense mechanism.
So for patients who want to avoid those long-term risks and who don't necessarily need round-the-clock maximal acid suppression, doctors often transition them down to famotidine.
It gives the stomach a break without shutting down the factory completely.
Hmm.
Hospitals also use it intravenously to prevent stress ulcers in critically ill patients.
Oh, and we should probably mention the COVID-19 observational quirk from the sources.
Oh, right. That was bizarre.
In the spring of 2020, during the height of the terrifying first wave in New York, doctors analyzing patient data noticed this weird signal. Hospitalized COVID patients who coincidentally happened to be taking famotidine for their severe reflux seemed to have better survival outcomes than those who weren't.
It was a desperate time, and scientists were looking for any port in a storm. The theory was that maybe famotidine, as a histamine blocker, was somehow blunting the massive immune overreaction, the cytokine storm, that was killing COVID patients.
It even triggered actual randomized clinical trials testing massive intravenous doses of famotidine.
It did. Ultimately, though, the rigorous trials showed it didn't work as a COVID treatment. The early signal was just statistical noise.
But for a few surreal months, an over-the-counter heartburn medication engineered in the 1970s was one of the most closely watched experimental therapies for a novel coronavirus.
It really highlights how the pharmacological tools we build can generate wild hypotheses decades after their invention. But, as we step back and look at the whole legacy of H2 blockers, I keep returning to the ranitidine recall.
It is hard to shake. It really makes you reconsider the whole concept of a safe drug.
This raises an important question. We operate under the assumption that if a medication has been used by millions of people for decades without incident, its safety profile is completely mapped out.
Right, that it's a known quantity.
But ranitidine shattered that illusion. It passed every FDA hurdle, it was monitored, it was a household name. Yet a fundamental, inherent chemical flaw, a molecule breaking down under the most ordinary storage conditions when completely undetected for over 30 years.
Which is terrifying.
It forces a very uncomfortable question about the mundane, everyday pills we swallow without a second thought today. What perfectly common medication sitting right now in your medicine cabinet might we discover a hidden, shocking chemical truth about 30 years in the future?
That is definitely something to think about the next time you reach for a quick fix. We put so much faith in the chemical memos we send to our own biology, but sometimes the paper those memos are printed on is inherently flawed, and it takes us decades to realize it. Thank you for joining us on this deep dive.